Friends, in this video you are going to learn electric potential energy in an external field. This means that what will be the work done in bringing charges in an external field. You will learn two cases for this. This is for case number 1, electric potential energy U of a single charge in an external field. So we required electric potential energy of a single charge in an external field. Let us draw a field. This is the electric field. Let electric field is E. E is electric field. Let us take a point here A where we want to bring a charge. So the distance from the origin of the source electric field is R1. Let this be R1. So potential here is V1, V1, VR1. Let the potential here is VR1. Now when you bring a charge Q1 here from infinite to this point, then this charge will faces a potential VR1. So work done in bringing charge Q1 from infinite to A is work is equals to Q1 VR1. This is the work done when you bring a charge, single charge in an external field. Now you are going to understand case number 2. In case number 2, potential energy of a single charge can be changes with two charges. Potential energy of two charges in an external field. So as you have just learned that when we bring a single charge from infinite to this point, then this charge will face a potential VR1, due to which here we have a work, and that work is W, and W work W1. Let it be W1. W1 equals to Q1 VR1. Now we want to bring another charge here. Let us bring another charge here. This point is B. So from the source electric field to the point B, let the distance is R2. So due to electric field here we have a potential, and potential is VR2 is a potential here. When you join, let us bring the charge, and at point B, due to charge Q1, here we have another potential which is V1. This is V1 is K Q1 by R12. R12 is the distance between A and B. R12 is the distance between A and B, R12. So when you bring a charge Q2 from infinite to point B, then the charge Q will faces two type of potential. One potential is due to charge Q1 and another potential is due to charge VR2. Let us write here Q2. So work done in bringing charge Q2 from infinite to B is work W is equals to, first the work is due to this potential, so this is equals to Q2 VR2. Second, due to this potential, so this is Q2 into V1. V1 value is already written, K Q1 by R12. So you can write it Q2, this is VR2 plus Q2, this is K Q1 upon R12. This is equation number 2. Let it be equation number 1. So total work done can be calculated by adding these two. Total work done. So total work done W is equals to W1 plus W2. W1 equals to Q1 VR1 and W2 equals to Q2 VR2 plus K Q1 Q2 upon R12. Now this work is stored in the form of electric potential energy U. So you have U equals to Q1 V R1 plus Q2 V R2 plus K Q1 Q2 upon R12. This is the expression for electric potential energy due to two charges. For understanding this equation, we require a numerical. Let us have a numerical. Suppose this is xy axis and this is axis. This is a point where the coordinate is 9 centimeter, comma 0, comma 0. Here we place a charge of -2 microcoulomb, and let here is a point where the coordinate is -9 centimeter, comma 0, comma 0, and here we place a charge of 7 microcoulomb. This is Q1 and this is Q2 charge here. Now there is no field, only we are placing two charges Q1 and Q2 at the coordinate 9 centimeter and -9 centimeter. Then the question is, what will be the potential energy required for putting these two charges in this assembly? Then the solution is very simple. It is U potential energy equals to K Q1 Q2 upon R12. R12 is the distance. R12 is this distance from charge this point to this point, and this is equals to 18 centimeter. So we will write here 9 into 10 to the power 9 into 7 into 10 to the power -6 into -2 into 10 to the power -6 divided by 18 into 10 to the power -2 in meter, because this is 18 into 10 to the power -2 in meter, and here micro stand for 7 into 10 to the power -6 coulomb. So this is stand for, this is equals to -2 into 10 to the power -6 coulomb, because micro for -6. Now solve this. 2 cancel, this 18 cancel, 9 cancel. So you have 7 -9 into 10 to the power. So you have this 2 -2 when moves to numerator side, it becomes +2. 9 plus 2 is 11, and here -6 -12 plus 11 is -1. So you have 0.7 with a minus sign joule of the energy. So case number first, you understand what will be the energy in this situation. Now I am giving you case number B, second question on the same parameter. The question is, if I want to separate these two charges to infinite, separate A and B to infinite, then in that situation what will be the energy required? So in that situation, energy delta U is equals to U final minus U initial. As they are separated to infinite, so at infinite the energy will be 0. So this is equals to 0 minus, here this is equals to minus 0.7, so this is equals to plus 0.7 joule is required. Now the third case, this whole assembly is put in a external electric field. This means that there is an external electric field, and the external electric field E is equals to A upon R square, where A equals to 9 into 10 to the power 5 coulomb per meter square. Now there is an external electric field E equals to A upon R square, and you have to bring these two charges. Then what will be the energy required? Number C part of the question. Now for that, first of all, these two charges when bring at these 2 points, then the energy required is 0.7 joule. This is due to the presence of these two charges there. So this will be not changed, this will be there. Instead of that, we have an additional thing. The additional thing is due potential energy due to electric field E at this point and at this point. So we know the equation of potential energy of electric field due to a system of charges. Energy U is equals to Q1 V R1 plus Q2 V R2 plus K Q1 Q2 upon R12. This is the equation we have find out. We know that potential V R1 is equals to electric field E upon R. We have electric field E is equals to potential gradient. So here we have V, this is equals to R. This is the general equation. So from this equation, you are going to write VR is equals to E into R. This is the equation. So you have VR1 is equals to E into R1. So what will be E? E is E from here. This is E equals to A upon R into R1. So this R is changed into R1 here according to formula, and R1 square. So this is equals to A by R1. The value of A is 9 into 10 to the power 5, and the value of R1 is 9 centimeter. So 9 into 10 to the power, it is minus 2. So 9 will cancel out. So you have 10 to the power 7. So potential equals to 10 to the power 7 volt. Similarly, you have to find VR2. VR2 equals to ER2, which is equals to E equals to A upon R2 square into R2. Cancel this again. So you have A upon R2. What is the value of A? The value of A from there is 9 into 10 to the power 5, and the value of R2, again the value of R2 is here 9 centimeter. So this is 9 into 10 to the power minus 2. Again 9 will cancel out. It comes to be 10 to the power 7 volt. So you get the value of VR1 and VR2, which is 10 to the power 7 volt. So in this equation, we write the value of charge Q1 is equals to 7 microcoulomb, 7 10 to the power minus 6, and this is 10 to the power 7 volt. VR1 is 10 to the power 7 volt, plus this is equals to minus 2 10 to the power minus 6 into 10 to the power 7 volt, and plus this is, after solving this, we already get the value of this is 0.7. So this becomes 70 minus 20 minus 0.7. So this becomes 50 minus 0.7. This becomes 49.3 joule. Thus, you have learned electric potential energy in an external field, and you have seen a numerical solving on this equation. Do like, subscribe and share my channel. Thank you.